And let's see, question. So yeah, the stuff we're doing this week is fair game for the exam. So we're gonna go through more of the material from the homework. The homework is not graded, um, because you would turn it in and we wouldn't have really time to talk about it. But yeah, this chapter is stuff that we could find on the exam, but only to the degree that we go through it in class, and that you see it on the homework sets. Um, Probably Friday, probably the last day of class, we'll talk in some detail about what you can expect on the final exam. All right, so let's do an attendance note in the beginning here. And any questions so far on grammars, the stuff we went through on Friday, which was mainly looking at analysis of phrase structure grammars. We haven't done synthesis yet. We're going to do that next. But any questions up front? Actually, I want to go through the homework first. All right, so let's talk about homework 8 first. So, oh no, there was no class on Friday or Wednesday. This was a week ago that we had class. So, yeah, so a week ago, last Monday, we started talking about grammars. And let me pull up the homework. All right, so this was the homework 8 that I've graded and given back. So question 1, adjacency list matrix and incidence matrix for the following. I didn't grade that one. I didn't grade 2, but I went ahead and graded 3. So 3 is a directed graph, and so you can take from or to however you like. But if we label these, let me copy this down onto paper. Actually, let me just go ahead and print this. So if this is the adjacency matrix, we can think of this as, you know, maybe label these A, B, C, D. That seemed to be what most people did. And so draw these somewhere. And so, you know, if we think of this as like from and to, then this one right here says there's an edge from A to A, so that's just a little loop. There's also an edge from A to B, an edge from A to C, and no edge from A to D. B only has an edge going to C, so that looks like that. C has an edge to A, so we come back that way, and C also has a loop, it goes to itself. And then D goes to A, B, and C, but not to itself. So it goes to C, it goes to B, and it goes to A. So that would be an example of the graph. And if I had labeled these, you know, W, X, Y, Z, obviously my graph would look different because W, X, Y, Z. Or if I interpreted it as saying that, you know, we're coming from this edge and to that edge, then all my arrows would be reversed. But the basic structure of the graph is the same. And you can do some quick checks on this. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines drawn. And if I count up the ones in here, 1, 2, 3, 4, 5, 6, 7, 8, I have 9 ones in my matrix. Each one corresponds to an edge, so the number of edges should be the same as the number of ones. So you can do some quick sanity checks on that. All right, so question 4 was looking at a pair of adjacency matrices and asking how they correspond to each other. Are they isomorphic? If they're isomorphic, we can find a mapping from these vertices to those vertices. So if we label this A, B, C, and label these X, Y, Z, and then we do the thing that computers can't do, some computers, which is draw the graphs for these. So A, B, C. So A has a loop and it also goes to C. There's a loop and A goes to C. B goes to itself and it also goes to C. So B has a loop and goes to C. And C goes to A and B. So C goes to A, C goes to B. So these look like symmetric matrices, so the direction of these doesn't matter. So if we draw the X, Y, Z, X has a loop and it also goes to Y. Y goes to X and Z. And Z goes to Y and Z. So it goes to Y and it goes to Z. And so here's the part that's harder for computers, right? We can look at these and we can say, yeah, I think these are kind of the same, right? If I take this one and I just put it like that, I've got a loop, I've got a loop, I've got this thing going to both of those. Yeah, these look like the same creature. And so A looks like, if I take my A and I change it to a Z, and I take my B and I change it to an X, and I take my C and I change it to a Y, this graph suddenly becomes that graph. And so this is what we call an isomorphism. It's a mapping from these vertices to those vertices, which basically gives me the same graph. And so that's enough to show that these two graphs are isomorphic. But just to kind of close the loop on this, here's our original matrix. This is the adjacency matrix for this first graph. If I apply this mapping, if I say let's take A and change it into Z, so A is going to become Z, and B is going to become X, and C is going to become Y. Well, you know, I've got a matrix written, but it's all kind of, you know, a wonky order. So let me bring my Z over to here, and let me write this as follows. I'm going to do X, Y, Z. And so here's X, 0, 1, 1. Here's Y, 1, 1, 0. Here's Z, 1, 0, 1. And over here I've still got Z, X, Y. And now let me bring this Z down to the bottom here and write this once more. But like this, X, Y, Z. So my X row is 1, 1, 0. My Y row is 1, 0, 1. And my Z should be 0, 1, 1. And so this, you know, is exactly the same as that. I'm just moving rows and columns around, but guess what? That's the adjacency matrix of the second graph. So what have we done? We changed the labels from A, B, C to X, Y, Z, and then we just rearranged the rows and columns. We didn't change anything. We just drew them in a different order. And when we did that, magically, we ended up with exactly the same matrix as this one. That's what it means for two graphs to be isomorphic. If you've done linear algebra, Math 215, you'll recognize this swapping of rows and columns. This is something we do when we solve simultaneous equations. We rearrange variables by moving the rows and columns of the matrix corresponding to a set of equations. It is magic, totally. All right, so then question 6 I looked at also. So is there an Euler path? An Euler path has to travel each edge exactly once. And so here's a path we can follow. I'm just going to start at A because it has an odd degree, and the other vertices have even degree except for one other. So I'm just going to start at A, going to come over here, come out here, come back up, come down. I can do this loop, and I can do this loop. And I've visited all of the edges exactly once. And there's different ways to do that. There's a lot of different ways to do that. I could go A and then do this loop, and then come down here and do this loop, and then go up there and come down like that. There's a lot of options. But again, if I were to draw this list of vertices in order the way I just did, it would be A, B, C, A, D, B, D, C, D. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. Every pair of vertices corresponds to an edge. How many pairs do I have? I have 8. And how many edges do I have in my graph? 1, 2, 3, 4, 5, 6, 7, 8. So if I'm going to have an Euler path, and I list all the vertices of that path, I better end up with 9 vertices. This is like a programming fence post thing, right? 9 vertices corresponds to 8 edges, because there's 8 pairs, right? There's not an Euler circuit, and you can be sure of that because even if this was an undirected graph, I have a node here, a vertex with an odd degree. And if the degree is odd, then I don't have a circuit. That's one of those easy to check things for Euler paths. For Hamiltons, we don't have such an easy check. But since I'm asking for a Hamilton circuit, we need to start and end at the same point. And we can pretty much convince ourselves the same way we did this example in class, similar example, that, you know, this is definitely going to cause us problems. Because if we start here with F, there's no way to come back and end at F, right? Because we would end up visiting this node E more than once. And if we don't start here, if we start anywhere else, we're going to have to come through E to get to F, and then go back to E to come back to wherever we started. So there's no Hamilton for this. All right. Anybody else who has a physics exam at 1:30 today, just send me an attendance ping before you leave, and that'll be good. And I'll post the lecture as usual. All right, Dijkstra's algorithm. So this one I definitely want to talk about. This will definitely be on the final, maybe, maybe definitely. And I want you to know this algorithm when you leave here. So I had a few homework submissions that, you know, laid out perfectly every step that was being done. It was very easy to see, you know, that the algorithm was being applied correctly. I had some submissions where there were, you know, maybe 2 pictures drawn and a lot of things crossed out, and I could kind of believe that maybe the person knew the algorithm, but it was a little hard to tell. And there were some where it was pretty clear that the algorithm was not being used perfectly correctly. So I want to go through this the way that you might write this up on an exam. Oh, thank you. Wow. Cappuccino and a blanket. Awesome. I've got my cozy blanket here. So let's write up this problem here, and I'm going to make a copy of this. And like I say, if I give you a question like this on the exam, I'll usually give you multiple copies of this graph that you're working with to help you with not having to redraw too much every time. Alright, so we're looking for a shortest path from A to F. So the first thing we're going to do is we're going to, visit the node that we're starting from, which is A. I'm going to write in tentative distances everywhere. So the initial tentative distance is infinity. The distance here will be 0, and the path to get there is just A. So that's our starting configuration. And since A is the node we're visiting, we're going to relax distances from A, which means 0 and 2 is 2, that's better than infinity. And the path here is AB. 0 and 3 is 3, that's better than infinity. And the path is AC. And I'm not going to change anything else on this diagram, because as soon as I do, I've lost track of what order things happened in. If I circle another node and I start relaxing more distances, I can't tell what happened where. So you don't have to redraw the picture every single step, but every iteration through the loop. All right, and remember our basic loop is visit a node, relax distances. So let's just add a third step. Draw a new picture. And then go back up here. So let me redraw my picture. So A is visited, distance is 0A, this is 2AB, this is 3AC, these are infinity. Alright, so now we're back to the top of our loop. We want to visit the closest node that we haven't already visited. Well, this node has a distance of 2, this has a distance of 3, these have distances of infinity. B is the closest node, so we're going to visit B. I'm going to circle it. And now I'm going to relax the distance to adjacent nodes. So 2 plus 5 is 7, that's better than infinity, so this is 7, A, B, D. 2 plus 1 is 3, so this is 3, A, B, E. And those are the only unvisited nodes adjacent to B, so we're done with the relax step. Alright, draw a new picture. I'm gonna get smarter this time. And reorient my page.
I think my problem was trying to do it all in one image.
Right, right.
Not that I didn't know the algorithm, but just trying to do it in one go is no bueno.
Yeah, yeah, and if you're doing this for yourself, you get a good eraser, you can totally do that. If you're just trying to like practice with the algorithm and so on. But then it's hard to grade. Alright, so this is still infinity. And I think everything else is set. Okay, so this was the image we had there. So we're back to the top of our loop. Visit the closest node that hasn't been visited yet. We've got a 3, we've got a 3. That should be a... sorry, that was a 2 plus 2. I took the 1 from there. 2 plus 2 is 4. So this is 4. So visit the closest node. That's going to be the C. And then relax everything. 3 plus 5 is 8, but 8 is bigger than 4, so we don't change that distance. Right? Relaxing means only update the distance in the path if it's better than what you've already got. If it ends up exactly the same, you could update it, but you're not going to get a better final answer. So we usually just leave it as it is. But if it was better, if it was a 3 or smaller, we would go ahead and update that. So the only thing we've done in this step is we've circled C. But if I go ahead and visit E now, I've gone from, this picture to one where I have 2 nodes circled. I don't know which order those were visited in. So you gotta do the writing again. So find a pen that you like writing with, or, make multiple copies of this. If you have like a nice, dip pen with a good inkwell, this is fun to do. Because there's a joy in writing and taking your time. Alright, so what's the next node to visit? Unvisited nodes, we got a 4, a 7, and an infinity. That's going to be our 4. And we're going to relax distances. So 4 plus 4 is 8. And the path here is A, B, E, F. 4 plus 1 is 5. That's better than 7. So we're going to ditch the 7. We're going to put in a 5 and say, hey, we can go A, B, E. And then D, get there in 5. Those are the only unvisited nodes we can relax from E, so we go on. And this may be the last one we have to do. So there's 0 to A, there's 3 for AC. There's 2 for AB. These are visited. Here's node E4 with Abe. Here's node D5, ABED. There's 8, ABEF. Visit the closest node. Sorry, that wasn't circled yet. Visit the closest node that's uncircled. That'll be D. So we visit that. And then we relax the distances. 5 plus 2 is 7. That's better than 8. So this becomes 7. A, B, E, D, F. And then I would draw this one more time. I won't do the whole thing. And I would just circle F. Because that's the only node that's left unvisited. And once we visit this node, we're done. Right? Even if we had other nodes that we hadn't circled yet, if we were trying to find the distance from A to F, as soon as we circle F, we found a best distance and path to that node. And then I would, final answer 7, and the path is A, B, E, D, F. Let's see. Oh, chats. It'll certainly have the possibility. How is C closer than E from B? So yeah, we're exactly. We're going with the one that's closest to A. So we've got these tentative distances. So we pick the node with the smallest tentative distance that we haven't already visited. That's the one we visit next. And those tentative distances in this case are the distances from A. And again, this is a good greedy algorithm, right? It always says, well, the closest city I can visit now is Portland, right? So I'm going to go to Portland because that's closest to where I started. And once you get there, it's like, okay, well now the closest place would be, Tillamook. And so it always picks up like a step that gets you, the greatest level of happiness if your happiness is based on trying to minimize path lengths, right? So that's a greedy algorithm. All right, so any questions on how to write, on the algorithm itself, or how to write it up for the final exam?
No, I'm pretty sure I just got, well, I should have drawn it about 6 more times.
Okay. Okay. And I see a name in chat that's not like a first name, last name, which is going to foil the attendance ping software. The term relaxing the node is confusing to me. Yeah, it's a strange term. Relaxing the node, we could rephrase that as once you visit a node, calculate the distance to adjacent nodes, assuming you can get here in 4, right? How long does it take to reach from here to another node? And if that answer is better than the distance we've written down so far, then we're going to change that distance. So right now it was saying, it took 8 steps to get to F. But down here we said, we can get to node D in 5 plus 2 is 7. 7 is better than 8, so that's called relaxing this tentative distance. And so replace that with a smaller distance and the corresponding path. Yeah, it's probably being on a different device. Because there's no last name. Let's see. If the distance from B to E was shorter, would we not have to visit C at all? So after we visit, go back. After we visit B, right? We don't look at what the distance from B to E will be, right? We choose a node to visit before we relax distances. So before we say 2 plus 1 is 3 is better than 4, we're going to say, hey, but 3 is better than 4, so we're going to visit C first. Because it could be that we have a path from here to F with a length of 1. And it could be that we have a path from here with a length of 1. And if we visit E next and we say that's 4, then we might take the 1 and say we can get to F in 5. But in fact, visiting C would get us to F in just 4. So yeah, the greedy part of it means that we need to visit the closest distance first. Probably generally you're going to end up visiting all nodes, but you're not visiting nodes just because you haven't visited them, right? If this was 30, then you would not visit C for a long time, right? You wouldn't visit C unless all the other nodes that were unvisited had a distance bigger than 30. So you take them in order. And this becomes more clear when you actually write code to implement this algorithm. And you basically rank your vertices in order of their tentative distance, and you pick off the smallest one. And one way to do this is to use what's called a heap. It's a really awesome data structure we'll do in 222 in winter. And that's one of the good applications for a min heap, is to implement Dijkstra's algorithm. All right. Let's see. So any other questions on that or on the homework? All right. So we talked on Monday about analyzing phrase structure grammar. So we had a grammar and we wanted to see what language it recognized. And so we, tried to create sample sentences starting with the start symbol and applying the production rules. That's the analysis piece. And so the trickier part is synthesizing, coming up with a phrase structure grammar that represents a certain language. So let's just try a few examples of this. So suppose we have some grammar G, and we're told that its language consists of the following: the empty string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So it's a certain number of zeros followed by the same number of ones. And we can paraphrase this as something like this. Right, we could say that this is 0 to the n, where 0 to the n means n copies of 0. So 0 to the 5 would be 5 zeros, followed by the same number of ones, 1 to the n, and we're specifying n's an integer and it's bigger than or equal to 0. So if n is 0, this is no zeros followed by no ones, that's the empty string. If n is 1, this is a single 0 followed by a single 1, that's this string. If n is 3, this is 0, 0, 0 followed by 1, 1, 1, that's this string. So this is a little bit more of a formal way of writing, you know, this without the dot, dot, dot on the end. And so we want to make a phrase structure grammar whose language is, you know, this. And so our vocabulary, remember this grammar is vocabulary, terminal symbol, start symbol, and production rules. So it's that 4-tuple. So our vocabulary is certainly going to include a 0 and a 1. It may include some other stuff, because we sometimes have these sort of intermediate symbols. But our terminal symbols are probably going to be 0 and 1. Our start symbol, we usually just make S, so we can put S in our vocabulary also. And then the secret sauce is our production rules. And that's the thing that sort of makes the grammar. So it's been a week since we played with analyzing these things. But what might we try for production rules? Any ideas? These productions are, you know, something, arrow, something. So they're rules that say we can change some collection of symbols into another collection of symbols. And we might start with this one, the empty string. Can you think of a production rule that would let us include the empty string in this language?
I was going to say one of the production rules we might be able to have is for every 0, you can turn it into n number of zeros plus 1, so like 0, 1, or 0 to 0, 0. Maybe?
Okay. So yeah, we want to be able to change 0 into 0, 0, and we want to be able to change 1 into 1, 1, right? So let's think about our start symbol. And we know we want to be able to get the empty string. So here's a sort of low-hanging fruit. We could just take our start symbol, change it into lambda, the empty string. And that would give us, you know, our empty string in our language. And the key here is we want to be able to add a 0, we want to be able to add a 1, but we want to be able to do those in unison. We want to make sure if we add a 0, we also add a 1, so that the number of zeros and ones is always the same. And if we have an empty string, we know it's the same because we have 0 of each. But if we're going to add a 0 and a 1, what would this do? And so this is getting into a little bit of that recursion mindset that we dabbled in with inductive reasoning and mathematical induction, and then with recursive formulas. If we believe that we're going to have a set of production rules where S is always a certain number of zeros followed by the same number of ones, well, if S satisfies that property, this will also satisfy that property. Because S will have, n zeros followed by n ones, while this will have n plus 1 zeros followed by n plus 1 ones. And this will still be something that we want in our language. And it turns out this is all we need for this language. So let's analyze this. Right? So what's the language comprised of? Well, certainly S can go to the empty string, so the empty string is recognized by the language. But S could also be a 0 followed by S followed by 1. Well, a 0 followed by S followed by 1. If S is the empty string, that's 0 followed by the empty string followed by 1. That means 0, 1 is part of the language. And so this, if this is an acceptable thing that S can be changed into, right? Well, we can also change S into a 0 followed by this, followed by a 1. And so this is a part of the language. And if this is something that S can be changed into, then our start symbol can also be changed into a 0 followed by this, followed by a 1. And we can keep doing this. And so this is going to be the language generated by that phrase structure grammar.
Where exactly would this be super useful? Out of curiosity.
So anytime you're doing any kind of intense parsing, so like in CSE215 we write a command line parser that lets you say, some character, space, some number, and it does something. That's a fairly simple kind of parsing. But if we wanted to do something more complex, if we wanted to, for example, recognize what a floating point number is, so that if the person types in negative 2.3 exponent negative 5, and we want to know if that's a valid floating point number, right? We could do some sort of syntactic analysis on it. And that's basically what we're doing here. We're looking at ways to characterize syntax. So any kind of parsing, including, if you wanted to write a compiler, if you wanted to do a command line interpreter for a shell that lets the person type in commands, if you wanted to write something that processes regular expressions. So pretty much any kind of syntactic analysis of text, this can kick in. And so it appears in all sorts of different areas of computer science. And this is a fairly kind of heady way to think about syntactic analysis. We'll see some other ways that are a little more down to earth. But this is kind of like the assembly language version of something we might do in C, for example. It's a fairly almost theoretical approach to it. So let's try a similar problem. Let's suppose that our language consists of 0 to the m, 1 to the n, where m and n are integers and they're each bigger than or equal to 0. So let's start off, let's just name some exact strings that would be part of this language. So using this kind of simplified notation or compressed notation for strings, what would be some strings that are part of L of G?
The empty string.
Because if m is 0 and n is 0, This is just the empty string. Good. What else?
It could be just 0 or just 1.
Just 0 or just 1. M could be 1 and N could be 0 or vice versa. Good. What else?
Get it 0, 1.
0, 1, because M could be 1 and N could be 1. Excellent.
Might as well also add 0, 0, 1, 0, and 1, 1.
0, 0, what else?
1, 0, and 1, 1. Or would that work?
Binary.
Oh, yeah.
Is 1, 0 a part of it, though?
Oh yeah. No, it's not.
Right, it's not.
No.
But how about this? Is that good?
Yeah.
Yep.
Yeah. So this is capturing the idea of a bunch of zeros followed by a different bunch of ones. And they don't have to be the same size bunches because we've got M and N. And those bunches could be, you know, 0, as in none of those symbols. But, you know, a bunch of zeros followed by a bunch of ones. So it's a pretty big language.
Technically, it could be a bunch of 1.
Sorry, your mic broke up. Say again?
Technically, it could just be a bunch of 1s.
Yeah, could just be a bunch of ones.
Yeah. But it could never start with 1 and end with 0, right?
Right. Once you have a 1, you're down at this part of the expression, and so you can't get any extra zeros in there. But you can do a bunch of zeros and then put in 0 or more 1s. So let's suppose our vocabulary is 0, 1, S, our terminal symbols are 0, 1, our start symbol is S, and let's think about production rules. So what's the one rule we kind of get for free?
S is S to lambda.
Yeah, S can go to lambda. That's an easy way to get that empty string in there. Suppose we just wanted a bunch of zeros. Forget about the ones for now. We just wanted 0, 2 zeros, 3 zeros, 4 zeros. So let's do a subproblem. So just a bunch of zeros. And same production rule, same vocabulary terminal start symbol. So S could go to lambda, but what else could we do for S? Let's do this one first, and then we'll go back to the other one. So any ideas?
S to 0S, maybe?
Hey, I like that. If we say S goes to 0S, it means we could have a 0 followed by a lambda, which would just be a 0. Well, if S can change into a 0, then S could also change into a 0 followed by that S, which is another 0. So S could be 0, 0. And so that's actually a perfect set of production rules for this. So for example, 0, 0, 0, we can think of this as a 0 followed by an S. Right? How do we know that 0, 0 is an S? Well, it's a 0 followed by an S. How do we know that 0 is an S? Because it's a 0 followed by lambda, which is an S. Right? Or we can go forward. We can start with S, and we could say from an S we can have 0S, and from this S we can have a 0S, and from this S we could have a lambda. And so 0, 0 followed by an empty string would be a string in this language. So this is a good set of production rules to get a bunch of zeros. So we could do this. But then we need something else, because we also want to be able to get some ones. So let's do a different sub-problem. Let's look at this language, just a collection of ones. So it looks like that.
So the idea of including S goes to the empty string in our production rules is that we have the option to terminate our string, right?
Mm-hmm. Yeah. Yeah, if we only had one rule, which is S is a 0 followed by an S, we'd never be able to actually write a string. We could say that S is, 100 zeros followed by an S, but we never have a thing that S is. Maybe we could have a rule that said S can change into a 0, and that would work. But if it doesn't take us to eventually a terminal symbol or an empty string, we're just going to keep making strings longer and longer and longer. And this, in some weird way, corresponds to that base case in mathematical induction. Alright, so let me use a different start symbol here. Let me use A. And then somebody suggested our production rules could be, we'll throw in the lambda anyway, but they said let's change A into a 1 followed by an A. And that's enough to capture this language, because it could be empty, it could be a single 1 followed by an empty string, it could be a 1 followed by a 1 followed by an empty string, and so on. So we've got this that captures a bunch of zeros, we've got this that would capture a bunch of ones, so let me go ahead and throw an A into our vocabulary up here. And we don't want our start symbol to change, right? But after we've got a bunch of zeros, we'd like to have a bunch of ones. So S can change into a 0S, but we could also do S changes into a 1 followed by an A, or maybe S changes into just a 1 for a single, and A could change into a 1, and A could change into 1A. That's probably overkill. But think about what this is saying. So my string could be empty, could be a 0 followed by an S, could be 2 zeros, could be a bunch of zeros followed by an S. So that's going to take care of, these 0 parts. And then I'm saying S can also change into a 1 followed by an A. So that would pick up a 1 right there. Or it could just change into a single 1. Or it could change into a 1 followed by another A. I'm not sure I need this at all. Oh yeah, I do need that one. So it can be a bunch of zeros followed by a 1, or followed by a 1, followed by a 1, or a 1 followed by another 1 followed by a 1, and so on. Or I could do A to lambda, and I could simplify some of this stuff. If I let A go to lambda, then I can get rid of some of these cases.
Can you combine S and A in the string itself? Like maybe S covers all the zeros and A covers all the ones, so it'd be like 0 S 1 A.
So yeah, I think we could make this a little cleaner. So let's do something like let's take S to AB, where A is going to be the zeros and B is going to be the ones. And A could be a lambda. A could go to 0 followed by A. B could go to lambda. B could go to a 1 followed by a B. And so S could certainly be empty because A and B could both be lambda. Or it could be a 0 followed by a lambda or a bunch of zeros. So this covers a bunch of zeros basically, including none. And then it's followed by B, which could be empty, could be a single one, could be two ones. So yeah, this would probably be a much easier set of production rules to think about. So yeah, that's a good idea. So there's a way to do any number of zeros followed by any number of ones. And so this is trickier, right? Trying to come up with production rules is harder than trying to understand what production rules do. But the process of doing this, and I probably won't ask you to come up with production rules on exam, I'll probably ask you to analyze some. So like, you know, look at this phrase structure grammar and tell me what the language is that's generated. But if you're trying to synthesize, right, you make a stab at it, you analyze the language, and if it's not quite right, you put something else in, or you change something or take something out. Analyze that language. And so when you do synthesis, you get a lot of practice with analysis, and the more you analyze these grammars, the more you sort of develop an intuition for how to do certain things, and you start seeing things happen again and again, like this idea of, well, let's break our sentences into two pieces, right, or three pieces, or a bunch of pieces, and let's just write, you know, some set of production rules for each of those pieces, and then string them together from the start symbol. And so you start to develop tricks and intuitions like this. So let's do one more of these. So I'm going to write the succinct form of this as a 1 followed by n copies of 0, 0, 0, where n is bigger than or equal to 0. So it could just be 1, or it could be 1 followed by 3 zeros, or 1 followed by 3 zeros followed by 3 zeros, and so on. And so these are all, you know, the decimal numbers that we have names for, 1,000, billion, trillion, and so on. So our vocabulary at least includes 0, 1 in the start symbol. The terminal symbols will be 0, 1. The start symbol will be S. And what do you think about production rules? Any ideas?
Would we be allowed to use some form of mathematics here, if we so chose to do so?
Like what?
Like, would it be against the rules of the language to say, a word in the language is 1 times 10 to the nth power, maybe?
Yeah, that would be
Would
a
that-
bit of a slick cheat.
Okay.
Yeah, because these are really just strings. But we might use a phrase structure grammar to be able to recognize, you know, powers of 10 where the power is a multiple of 3, for example. Alright, so somebody said S goes to 1. That's definitely part of the production rules because we want to be able to recognize a single 1.
S goes to 1, 0.
So 1, 0 wouldn't be quite right because 1, 0 is not a part of this language. any string in here has to be a 1 followed by some multiple of 3 zeros.
Oh, that's okay.
But this is close to something we could do, yeah. So someone said S goes to 0, 0, 0, and that's not exactly going to work because this is not part of the language. A 1 followed by this would be. So S goes to S followed by 3 zeros. And that works for, you know, a 1 followed by 3 zeros, but if this is something S can change into, then this would say S could become a that followed by another 3 zeros. And if this is something S can become, then it could become this followed by another 3 zeros. So that looks like a good piece of the production rules. So that should work. A different approach might be to add another symbol and say S goes to 1 followed by A, where A is going to be a triple of zeros. So A could go to lambda, or A could go to 3 zeros followed by an A. And that would work also, and that's using the idea of what we did in the previous one where we said, okay, this is going to capture that 1 in the beginning, and this A is going to capture the sets of triple zeros. And then we just wrote some rules for, you know, repetitions of 3 sets of zeros. So A is lambda, or it's 3 zeros followed by A.
So, quick question for
Yeah.
clarity here. Going from the first word to the second word, so 1,000 to 1,000,000 there.
Mm-hmm.
How does that work again?
So if we use this set of rules, let's derive, starting with the start symbol, S can be changed into an S followed by 3 zeros. And this rule says S can be changed into an S followed by 3 zeros. And we've still got these 3 zeros at the end.
I gotcha.
And that
I see
says
now.
S can be changed into a 1. So you can play with those. There's some examples in the book, I believe, that play around with this. It's towards the end of the book. And you can make these up yourself, right? You can just pick a pattern of, doesn't have to just be 1s and 0s. You could use more characters, but you describe what you want in a language and see if you can come up with production rules for it. And it gives you practice with, you know, deriving from a start symbol different strings. And there's a lot of detail, right? This is an entire semester course at a university, automata theory. But this is a pretty high level pass. And there's a lot of details. There's different types of grammars that we can talk about, and they have different impacts when we try to use these things to implement code. For example, we can write recursive functions in C pretty easily that will let us take a string and tell us if it's recognized by this grammar. This is how we could do syntax checking in the beginning of a compiler. And it turns out that if we write something like this, it's going to work really well. And if we write something like this, we're going to run into a bit of problems. Because depending on how we write our code, this is going to say, okay, if I want to know if my string is an S, let me see if it starts with an S. And it's going to make a recursive call and say, okay, does my string start with an S? Well, let me see. Does it start with an S? And it'll say, well, I don't know. Let me check my rules. Okay, is it an S? Well, maybe if it starts with an S, it is. So let me see if it starts with an S. And this is going to blow up our stack. We're going to recurse forever. This, on the other hand, every time we say, could it be an A? Well, it's got to start with 3 zeros. It's going to cut 3 zeros off the string that we're processing and see if the rest of it is an A. And so each time that we check to see if this rule applies, the string that we're checking the syntax of will get shorter and shorter. And so there's different types and classes of grammars that would specify, you know, whether this situation occurs or that situation. And so lots of detail. And like I say, you know, my undergrad, we did a whole course on automata theory, and it was a semester of all these details, and I didn't understand most of it, but it was cool to talk about anyway. But this is a high level view of it, and it's one way to talk about parsing. Are we going to discuss finite state machines for this week's homework? Yeah, we'll get to finite state machines sometime this week for sure. And the homework's ungraded, so, you know, do it as we go through the material and submit it, or come by office if you want to talk about it. But we'll get through it today or Wednesday. All right. Backus-Nauer form, BNF. This is a totally different approach to describing syntax. And I think I have some examples of this. Let me see. We got to do BNF. We got to do finite state machines. Turing machines. And we've got 25 minutes. I'm going to skip over BNF other than to give you a very quick overview of it. BNF is a way to describe syntax with a series of rules, and our rules mostly look like this. We'd list some kind of identifier, and we'd say this is equal to, you know, something followed by something, or, you know, something else followed by something else, or maybe something else. And then we could list what each of these things is in the same form. And it's similar to a phrase structure grammar, but a little more human readable. So for example, here's a set of BNF. It's the BNF for the language C. And so, for example, a type specifier is either the word void or char, short, int, long, float, double, signed, unsigned, or a structure or union specifier, or an enum specifier, or a typedef name. A structure or union.
What does BNF mean again?
Backus-Nauer form.
Backus, okay.
Yeah, it's two names. And everyone just calls it BNF. So a structure or union specifier is a structure or a union followed by an identifier followed by curly brackets, structure declaration, plus sign, or it's a structure or union, structure declaration, or it's a structure or union followed by an identifier. And structure or union is the keyword struct or the keyword union. And so each of these things declares, you know, what something is in terms of other things, and those other things get broken down further and further and further. A pointer is a star followed by a type qualifier, followed by a star, followed by a curly brackets pointer and a question mark. And these are weird to look at first, but when you start writing these for a language, you start being able to read this. And if you can read these things, if you can write these things for a language, it's very straightforward to write a parser that will take an input string and tell you whether it matches this syntax. And there's a slew of Unix tools that do this. There's Lex, there's Yak, I think Bison, and a whole bunch of other tools. Yak is yet another compiler. And it's a tool for compiling compilers, right? So if you want to write a compiler, you don't have to really start from C and say, you know, integer I equals 0. You can write a description of the language you want to compile and then run it through a tool like Yak, and it will create a compiler for you. Because, you know, writing a compiler is fun, but eventually people get tired of it. And so you write a piece of software to do it for you. That's what computer science is. It's laziness. Um, so these are fun to play with, but they would take us probably the rest of the class, and I want to get started on finite state machines so that we can definitely get to Turing machines and some computability on Wednesday.
So that's like a formal declaration of all the grammar in C.
Exactly. Yep.
Okay.
Yeah. So if you want to know what a jump statement looks like, it's either go to identifier or continue break or return, possibly followed by an expression. And this is 4 pages, and that's all of C. It's the whole language. So that's fun stuff. So here was some code I wrote back in college to parse out an expression, an arithmetic expression, right? And this was the BNF that I used for it. So it's a left expression, an operator, an expression, or a left expression, or a minus sign followed by an expression. It handles parentheses and so on. And this is the translation of this BNF into a series of recursive calls. So these are macros in C. Right, there's the empty string lambda. And this little piece of code right here parses arithmetic expressions. I can type in, a plus b times parentheses c minus 2 times d, close parentheses. It'll tell me if there's any syntax errors. And, it's a few dozen lines of this stuff derived from this stuff. So BNF is a fun thing to play with. And yes, someone said a while ago in chat, this reminds them of regular expressions. This is totally regular expressions, right? It's absolutely related. And the stuff that drives regular expressions is a lot of these kinds of mechanics. Alright, let's talk about finite state machines, and I promised you no flip-flops anywhere in sight, so I will try to stick to that. Let's think of a finite state machine more abstractly instead. As a set of 4 tuples, right? A present state, an input, a next state, and an output. We know these from those really wide tables we make in Engineering 250, right? So we're not going to make those tables here, but the concept is still, we have a present state and an input value, and based on that, we go to a new next state and we generate an output value, where those could be multiple inputs and outputs. And so, for example, here's a 4-state machine. And I'd be shocked if anybody recognized this from Engineering 250. But this was the mood machine.
I recognize it.
Excellent. So this is the happy mood, this is the neutral mood, this is the really sad mood, and this is like the don't want to wake up mood, right? And our input, 1 means it's sunny, and 0 means it's rainy. I like rainy days actually. But that's okay. So the idea is, right, if it's sunny, if you're really happy right now and it's sunny, tomorrow you're going to be really happy too. If you're happy and it's rainy, tomorrow you're going to be kind of meh. And then if it gets sunny, the next day you'll be happy again. If it's rainy, then you're going to be kind of like, ugh. And then if it's rainy again, you're going to be like, don't wake me up, right? So this is a 4-state machine that we could think of as predicting our mood. This is also a weather machine. right? When you cut through all of the linear algebra and the dynamic models and so on, one of the most accurate ways to predict tomorrow's weather is to use today's weather. If it's rainy today, just say it's going to be rainy tomorrow. People will think you're great at predicting the weather. And so you know, these are our rainy predictions. These are our sunny predictions. And if it's sunny today, and the sun is out, we're going to say, yeah, it's going to be sunny tomorrow. If it's sunny today but it's raining, we're still going to say, you know, it's sunny tomorrow, but we're not going to be as certain of it. And in particular, if it rains 2 days in a row, we're going to change our prediction to say it's going to rain, it's going to rain. Okay, this is also something called a branch prediction circuit. In particular, a 2-bit branch prediction. So you have an Intel or an AMD processor inside your laptop or desktop. It's got one of these circuits inside. And it uses it to try to predict the future. When there's a conditional branch coming up in a few instructions, it would really like to know ahead of time whether you're going to branch or not. And so it basically uses this kind of state machine. And it says, hey, the last time I was here, I didn't branch. I don't think I'm going to branch this time either. If it guesses wrong, it'll move to this state. And it'll still say, you know, I don't think you're going to branch. If it guesses wrong twice, it'll come down here and change its prediction the next time. So state machines get used all over computer science. They get used all over in hardware. We build state machines to basically track things that have happened and affect the behavior of the system based on past history. And that's really what a computer is. A CPU memory system is really a very, very sophisticated state machine. It has a ridiculous number of states. It's still finite, but the state is basically the collection of all the history of every past event. And in this case, you know, we've only got a 2-bit memory because we have 4 states. On a 16 gigabyte PC, we've got 16 billion times 8 bits worth of memory. But it's still basically a state machine. And so we can use state machines for a number of things, including recognition of input patterns. So parsing. So let's look at a state machine that does pattern recognition. Alright, so here's a state machine. I'm writing these a lot more sloppily than we do in Engineering 250, so I'm letting myself put, you know, instead of 2 arrows, I've just got an arrow labeled 0, 1. So I'm going to start off in the start state. If I have a 0, I'll move to this state. If I have a 1, I'll move to this state. And from that point, if I have a 0 or a 1, I'll move to this state. And once I'm here, a 0 or a 1 takes me to this state. Alright, I also have 1 or more states with a double circle on it. This double circle, that's what we call a recognized state. And so the question here is, what sorts of input strings will take me from my start state to my recognized state? Any string that does that, we call that a recognized string. It's a string that's accepted by this parser. So some of my recognized strings, for example, just the string 0 would take me from my start to a recognized state. A single 1 will not take me there, but a 1 followed by a 0 would take me there. A 1 followed by a 1 would take me there. And once I'm recognized, any 0s or 1s after that, I'm still recognized. So also 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, etc. Also 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, and so on. And also 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, and so on. So lots of strings that this machine recognizes. In fact, very few strings that it does not recognize. It doesn't recognize a 1. I think it recognizes everything else. But we could build a state machine. We could do flip-flops, or we could do this in software, you know. That would basically take an input string, and every time we get to the state, it turns on a light that says, hey, I recognize that string, or it sets a flag in software, right? So this is another way to parse input. And so we could say this recognizes the strings 0, 1, 0, or 1, 1, followed by 0 or more repetitions of a 0 or a 1. And this is getting really, really close to a regular expression now, right? That asterisk after something says there's 0 or more repetitions of this. And if these were square brackets, like in regexes and Unix, right, we'd basically have a regular expression. All right, let's do one more state machine. So here's our start state. And here's a recognized state. There's a 1. There's a 0, there's a 0, and there's a 1. So what are some strings recognized by this? Give me a few answers and I'll let you go for the day. So how can we get from the start state to the recognized state?
You could have 0, 1, 0, 1, 1, 0, 1, 1, 1, 1 so far.
Alright, 0, 1, what was the next one?
0, 1, 1.
Mm-hmm.
0, 1, 1, 1. Like, you could have an infinite number of ones following a 0.
Cool, perfect. What else?
Can't you have an odd number of zeros and any number of ones?
So 0, 0, 0. And then any number of ones, so 0, 0,
Yeah,
0 would
the
bring
ones
us back there.
Can be anywhere. So it'd be 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1.
So 0, and then the 1, and then the 0, and then a bunch of 1s, and then the 0, and a bunch of 1s. Perfect. So how would we paraphrase this? Oh, someone already did this in chat while I was yakking. Any string that has an odd number of zeros. Alright, so that's kind of a cool machine. You can put in binary strings and it'll tell you if it's got an odd number of zeros. It's counting, and it's doing modular arithmetic, and it's telling us if that count is congruent to 1 mod 3. And there's no limit. We can do more than 4 billion of these zeros, and it'll still keep track of them accurately. If we do this with a C program, it's going to lose track after 4 billion if it's a 32-bit machine, because our counter, you know, only goes up to 4 billion or 2 billion. And this will work on an infinite length string, right? It'll just keep moving states, and it'll always tell us, have I seen an odd number of zeros? That's kind of cool. All right, so think about that. And again, you can try some problems like this on your own. I think there's some homework questions on it. And we'll leave that for now, but Wednesday I want to do 1 or 2 more examples of this, and I also want to look a little bit at how we can modify strings with state machines. And then I want to talk about Turing machines, and the Turing machine is a particular model of a state machine. And it's the one from which, in some way, all of our current computers came from, this idea of a Turing machine. So we'll talk about Turing machines, We'll see what some programs look like in a Turing machine. And then we'll segue from that into notions of computability, and we'll get into this whole PNP business and halting problems and all the weird stuff. And we'll do a weird Wednesday instead of a freaky Friday, because Friday we'll do review for the final. All right, that's all I got today. So go ahead and send me an attendance note on the way out, please, and have a great afternoon. And I will see you all next time.
Bye.
Have a good.
Great day.
All right, thanks. You too.